Welcome back to Math 104. We were looking at a crucial example of a population standard deviation, which arose from counting the number of successes in 3 Bernoulli trials. In particular, an ideal dataset for the experiment of flipping a fair coin 3 times and counting the number of heads. We computed that the population mean equals 1.5, and the population standard deviation equals 0.8660. Do our shortcut formulas really work? Well, yes, we already know that the n times p shortcut works to compute the mean, but what's new is that this square root of np1 minus p shortcut really does work to compute the standard deviation. When we substitute 3 for n and 0.5 for p in the formula, being careful to compute this product before we compute the square roots, it turns out that the shortcut gives us the same numerical value as we obtained by doing the full long computation. Why is this important? It's important because we have shortcut formulas that enable us to compute mu and sigma for the special kind of dataset that arises when we count the number of successes in a certain number of Bernoulli trials. Thus far, the scenario has been that we are given a set of data, and the standard deviation is a number we compute for that set of data. We compute it by plugging all the data points into a certain formula, carrying out a computation, and we get some number at the end. That's standard deviation. And frankly, crunching out that computation of standard deviation is not that exciting. What's much more interesting is what we can do with this number. We can ask, what does this number we compute say directly about the dataset? The idea is to view the standard deviation as a measuring stick. In particular, each data point is a certain number of standard deviations above or below the mean. For example, in section 1, the mean final exam score, the population mean, is 74.57, and the standard deviation, the population standard deviation, is 8.01. Now, Pat received an 84 on the exam. We can ask, how many standard deviations above the mean is Pat's score? So here's the mean, 74.57. Here is Pat's score, 84, and we can ask, how much better than the mean did Pat do when measured in standard deviations? Every 8.01 exam points equals 1 standard deviation. This distance covered by the red braces, that's 1 measuring stick, 1 standard deviation. Apparently, Pat's score is more than 1 standard deviation above the mean, but less than 2. Let's think how to answer this question. In points, Pat's score is 84 minus 74.57 points above the mean. That's just how many points above. But I now need to divide by 8.01 to convert the units from points to standard deviations. So Pat's score is 9.43 points above the mean, divided by 8.01 to convert to how many standard deviations, and that's approximately 1.1773. Pat's exam score is 1.1773 standard deviations above the mean. And that agrees with this picture. 84 is a little bit more than 1 red measuring stick above the mean. Let's practice this idea some more. Alex received a 72 on the exam. How many standard deviations below the mean is Alex's score? In order to do these computations in a consistent way, we're always going to compute data point minus the mean. The fact that Alex received a score below the mean will show up as a negative number of standard deviations. As before, we compute score minus the mean divided by the standard deviation. This difference is negative 2.57 points, so Alex scored 2.57 points below the mean. This turns out to equal negative 0.3208. Alex scored approximately 0.3208 standard deviations below the mean. Okay, that gives us a new way of talking about how each student performed in relation to the class average. We've changed the units from points to standard deviations. Now that we know how to do that, we can go on to ask, what is the range of scores which are within 1 standard deviation of the mean? They might be less than the mean, they might be greater than the mean, they might even be equal to the mean, but the difference is at most 1 standard deviation. What is this range? This range is between a certain score and a certain other score. At the low end, to be within 1 standard deviation of the mean, that means the score can be anywhere from 74.57 minus 1 standard deviation up to 74.57 plus 1 standard deviation. Any score that falls within this range is within 8.01 points of the mean. The low end of this range is 66.56, and the high end of this range is 82.58. Any score falling between these two numbers is within 1 standard deviation of the mean. It differs from the mean by at most 1 measuring stick, by at most 1 standard deviation. Now, even though all the actual scores are whole numbers, we're going to allow decimals in answering this kind of a question. We're going to want to be in the habit of working with the exact range that represents 1 standard deviation on either side of the mean. But now let's understand exactly which scores actually fall within this range. They're all the scores starting with 67 and running through 82. So a score of 66 is outside of this range. A score of 66 is below the mean by more than 1 standard deviation. It's beyond this cutoff of 66.56. And this range of scores will contain everything up through 82. If there were any 83s here, they would be outside this range. All of these scores are within 1 standard deviation of the mean. Now that we've identified that range of scores, it makes sense to ask what percentage of scores are within 1 standard deviation of the mean. It's quite a large number of them, well over half in this case. And to find the exact number, we could count up all the numbers inside this box, or we could count up the number outside the red box and subtract from 100. Actually, because of the way this is arranged in columns of 10 numbers each, it's not so hard to count within the box. There are 1, 2, 3, 4, 5, 6 full columns, that's 60 numbers, plus an additional 6 here, from 67 through 68 in this first column, plus 4 more, these 82s. That's a total of 60 plus 6 plus 4 equals 70. Thus, there are 70 scores out of 100, which is 70% of the scores. We could also ask what percentage of scores are below the mean, but within 1 standard deviation of the mean. In other words, between 74.57 minus 8.01 and just 74.57 by itself. This we noted was equal to 66.56. So we can ask what percentage of scores are between 66.56 and the mean. We have the same lower cutoff as before. We're now counting all the scores starting with 67 and going up through 74. We are not counting 75 because the 75s are outside of this range. So the scores from 67 through 74, the ones that I'm enclosing here in blue, are not exactly half the number enclosed in red, but they're close. When you count up, there are actually 37. This percentage is 37 out of 100 scores, or 37%. Not exactly half of 70%, but close. Before going on to the next video, answer the following questions. What is the range of scores which differ from the mean by at most 2 standard deviations? Think what that means. They differ from the mean, they differ from 74.57 by at most 2 sigmas. After you find the range of scores differing from the mean by at most 2 standard deviations, then say what percentage of data points, what percentage of scores differ from the mean by at most 2 standard deviations.